All right, everyone. So I want to go back here. So I asked you to review the video on formal charges. You can also learn it from the textbook. It was in section 1.4. But I want to just practice some of that with a few examples. All right. So I want to do here is calculate the formal charge on the various atoms. All right. So the oxygen atom, well, you're supposed to, when you calculate formal charge, you're always given a structure. So you see the number of bonds to each atom, but you also, to be able to calculate formal charge on an atom, you have to know how many lone pairs are present, right? You won't be able to do it otherwise. So I really needed to show that, okay? So we can go through it for oxygen, but it may be easier just to remember that we showed that neutral oxygens, when an oxygen is neutral, it forms two bonds and it has two lone pairs. And that's exactly what this oxygen has. It has two bonds, one to carbon, one to hydrogen, and two lone pairs. So that's a neutral oxygen. There's no charge on it. And likewise, this carbon is neutral because we saw that a neutral carbon forms four bonds. And this carbon has four bonds, so that's neutral. The hydrogens, of course, are neutral because we learned that the neutral hydrogen forms one bond. Okay. So the only one that looks like it's not neutral is this carbon because it's not forming four bonds. So that sticks out. So let's see what the charge is on that carbon. And the way to do that, of course, is you draw a circle around the atom. You include the lone pair in the circle. And then you bisect the bonds to the atom. You cut those in half, right? And then you do your calculation. So formal charge equals the number of valence electrons in the neutral atom. And since carbon is in group 4A, it has four valence electrons. You subtract the number, the total number of non-bonded electrons, which is two, right? There's one lone pair. So we subtract two non-bonded electrons. And then you subtract half of the number of shared electrons. Well, half of a bond is each bond is two shared electrons, so half of that would be one. So you can just as easily just subtract the number of bonds. It's the same thing. So there's three bonds to carbon, so minus three bonds. So we have 4 minus 2 minus 3 is minus 1. So this carbon is a negative carbon, okay? Carbon anion. Okay? Carbon anions, as you can see here, have three bonds to the atom and one lone pair. Okay? So let's do the same for the next one, the nitrogen. We're going to do, right, bisect the bonds, circle the atom, and include the lone pairs. So nitrogen is in group 5A, so it has five valence electrons. By the way, it's probably a good idea to download a copy, print out a copy of the periodic table that I have posted to Canvas, so you can, often we will need information in that table, or else have it on a device that you can regularly check. So we have five valence electrons in neutral atom. There are two lone pairs on the nitrogen. That's four non-bonded electrons, right? And there are two bonds to the nitrogen, to the two hydrogens. So we have minus two bonds. So we have 5 minus 4 minus 2 is 5 minus 6. This is also the nitrogen's minus 1. Yeah. Okay. So it's pretty straightforward. The last one, carbon is neutral because it has four bonds. The hydrogen's neutral because it has one bond. But this oxygen is not neutral, right? Because if it were, it would have two bonds and two lone pairs. So let's see what it is. So oxygen is in group 6A. That's 6 valence. We have 1 lone pair on it, so that's 2 non-bonded, right? And there are 3 bonds to the oxygen, a triple bond. So 6 minus 2 minus 3 is +1. So that's a oxygen has a +1 charge, right? So that's it. That's a circle method is, I think, a very straightforward and easy way to calculate formal charge, right?
I have a question.
Yeah, please.
So on a test, how would this be given, how would this be given? Like, would you give us like the molecular formula and then we have to draw out the structure and then calculate the formal charge, or you would just give us the drawing?
Normally, with problems with formal charge, you would have the structure. You see the structure, and all the non-bonded electrons would have to be shown too.
Okay, so we wouldn't have to draw it out ourselves.
No, not in problems like this. Usually, you'll be just directly dealing with the structure. Okay.
Okay, thank you.
You're welcome.
Professor, to carry on her, then would we be given the specific atom to like calculate it on, or do we have to figure that out as well?
Well, I mean, for example, take this structure over here, right, that we did first. You should be able to assign formal charge to every atom. You should be able to determine like the oxygen and this carbon are neutral, right? Either by remembering the bonding rule for neutral atoms, or by just calculating by the circle method, right? You should.
So
Does that make sense?
So basically the one that stands out then?
I'm sorry?
Basically calculating the formal charge on the one that stands out, that's not...
No, all of them. You should be able to calculate the formal charge in all the atoms. So we know this one is neutral, right?
Right.
The easiest way is to remember the bonding rule for neutral atom, but if you forget it, you can always do the circle method. 6 valence in oxygen minus 4 non-bonded minus 2 bonds, right? If you forget the bonding rule for neutral atoms, you can always just go back and calculate it. Okay. Let me show you the next slide. I think maybe will provide a little, flesh this out a little more. Okay. So let me clear this and go to the next slide. So I'm going to show you the formula for formal charge again. Oops, sorry. So the formula for formal charge, right, is formal charge is equal to, the number of valence electrons, right, in the neutral atom, right, minus the number of non-bonded electrons around the neutral atom. And I'm going to just call it minus the number of bonds, right? So that's the equation. Okay, so in the previous slide, we were shown a structure, and you'll always have a structure. You have to have a structure. And so you know the atom you're trying, or atoms you're trying to calculate formal charge around. So you then know the number of valence electrons around those atoms when they're neutral from the periodic table. You have the structure, so you can see the number of bonds to the atom. And then you'll know the number of non-bonded electrons, if any, around the atom, because that has to be shown as part of the structure. Right? So in the previous slide, we had all these variables, and we just calculate formal charge, right? But it turns out the convention in chemistry is when you show a structure, the convention actually is you always have to show the formal charges, but you don't have to show the non-bonded electrons. And so what we have then is that in a typical structure that's drawn, you will see the structure, so you'll know the number of bonds. You can see the number of bonds to the atom. You have the structure, so you know the atoms involved, so you know the valence electrons around those atoms when they're neutral. And you will be given the formal charge, right? So in that case, the variable x is the number of non-bonded electrons. You just solve for that, okay? So let me show you. Let me show you an example of that. So let's take this structure here. So let's look at that carbon, which we know it carries a positive charge. And so ask ourselves, are there any non-bonded electrons around it? So let me just remind you that the convention in chemistry is when you're given a structure, you always have to show a formal charge around atoms that have it. But you don't have to show the non-bonded electrons. They're often omitted, and the reason they can be omitted is because they can be calculated from this equation. So let's calculate it. It's the same thing. You just have the variable is the non-bonded electron. So you have 4 valence in the carbon. X is, I'll leave the X for the last variable. The number of bonds to the carbon is 3, right? And now X is the number of non-bonded electrons, which we don't know, right? And so we can, that's equal to the formal charge on that carbon, which is given as +1. We have 4 minus 3 is +1, minus X is equal to +1. So you see X is 0. Right? So that positive carbon does not have any non-bonded electrons. It just has 3 bonds. It's an example of a species that does not have an octet. You may think, well, can it exist? And the answer is yes, it does exist, but it's very unstable. It's very reactive. It generally is formed in reactions and then immediately reacts with whatever's around. Okay. So in the same way, we can, let's say, calculate the number of non-bonded electrons around the fluoride ion. You may know that answer, but let's do it. Okay. So fluoride is in group 7A. So the charge you see is -1, it's given. So -1, I'm going to write it in a linear form. -1 is the charge on the atom. There are 7 valence electrons in all halogens. They're in group 7A. There are no bonds, right? No bonds to it. And then we're trying to calculate the number of non-bonded electrons, which is now the unknown X. So -1 is equal, -1 is 7 minus 0, or 7 minus X. X has to be 8. So X is 8. So the fluoride ion has 4 lone pairs of electrons. Okay. See how you do that? It's very straightforward. It's done using the same equation, but now the variable is the number of non-bonded electrons. All right. We can do one more. Let's do the borane, BH3. So I'll draw the structure. So here, I forget, I'm sorry, someone asked, you know, in this, do you ever have to draw the structure? Well, in this case, I guess you do. But there's only one way you can draw the structure BH3, because hydrogen only forms 1 bond, right? So it has to be like that. Right? So remember, in this case, we're trying to identify lone pairs. And in that case, the formal charge, if it were present, would have to be shown. So there's no formal charge here. So we can just do the circle method. Now, if you looked at your periodic table, you would see that boron is in group 3A. So the formal charge is 0. There's no charge. So it would have to be shown. Boron is in group 3A, so it has 3 valence electrons. There are 3 bonds to the 3 hydrogens. And then we're calculating if there are any non-bonded electrons, right? So you see 0 is 3 minus 3 is 0. So X is 0. So BH3 is a compound called borane, is like this positive carbon we just did before. It only has 6 valence electrons around it, the 3 shared bonds. It doesn't have an octet, and borane is likewise extremely reactive. it's a gas, and in fact, if you expose it to air, it bursts into flame spontaneously. So, but that's a real species. Right? So you have to be able to go either way, either calculate formal charges when you're given structures and show them the lone pairs, or calculate the number, know how many lone pairs are on an atom when you're given the structure and the formal charge, okay? Which is, as I said, the more, the conventional way of representing structure, okay? Okay. Any questions about that? Okay, so I'm gonna clear this. All these slides are posted, of course, and I'm gonna clear this and move to the next slide. So this is the polar covalent bond. There's a series of slides. I posted a video recording of these slides. I'm not going to go over it in class. It's covered in section 1.5 of the textbook, and you can also look at the video. So I'm not going to do that here today. Okay? But I want to look at orbitals and bonding in a little more detail. This is continuing our review of general chemistry as looking at the things that are the most relevant for organic. So, you know about atomic orbitals. In the 20s, quantum mechanics was established as a theory to explain that electrons have wave-like properties. They behave like particles sometimes, but they also behave like waves. They have wave quality. And the solution to these equation describes the wave-like properties for electrons, results in these visual pictures called electron orbitals. And this is a picture here of on the bottom of an S-type orbital. You've seen that before. It describes, an orbital describes the volume of space around the nucleus where the electron is most likely to be found. The orbital is the volume of space where it's a 90% probability that the electron will be found there. Right? Remember, according to the Heisenberg uncertainty principle, you can know the energy, the exact energy of an electron, but you can't know its exact position. You can just give a probability function of where it might be in space. It's very weird, of course, but it's the theory is extremely powerful and useful. So that's an s orbital, and you probably recognize these as p orbitals. Degenerate in chemistry means equal energy. Okay. Okay, it just means equal energy. And you see the p orbitals are shaped kind of like dumbbell shape, and their only difference between them is their spatial orientation. They're oriented along the x, y, and z axes, right? So those are the only orbitals we have to be concerned with in organic. You don't have to worry about the d orbitals and so forth, just the s and p. So I'll tell you about these colors and what they mean in a minute, okay? So as I indicated, electrons were shown to have wave-like properties, and just like a wave on a lake or a sound wave. And if you're looking at a wave, let's look, this here depicts it as a wave on a lake or in the ocean. You see the wave, you have part of the wave is above the surface. That's said to have a positive amplitude. It has a positive amplitude, and it's denoted by the color red. Okay, and then there's a part of the wave, there's part of the wave that's actually below the surface, and that's said to have a negative amplitude. And here it's coded in blue, right? And the part of the wave that doesn't move, that's on the surface is said to be a node. It's said to be a node, okay? So the colors in the previous slide don't represent charge, they represent the phase of the wave, whether it has a, at that point, whether in space, whether it has a positive or negative amplitude. And so I'll show you this thing. So here's a p orbital again. So the red is a positive amplitude, and the blue represents the negative amplitude of the wave equation that describes the orbital. I mean, that's really all you need to understand it on that level. And the node is the point where there's no electron density. There's no electrons at that point. The electrons are in this spatial region. So now I'll show you how waves are relevant for bonding. So when two atoms come together, the electrons are in orbitals, right? So those orbitals have to interact, and they can interact in two ways. They can reinforce each other. So if the electron in the orbital of this atom interacts with this one, and they both have a positive phase, they're in phase. When they're in phase, the orbitals you get what's called constructive interference. You result in the waves reinforcing each other, and you get bonding. You get strong bonding. It's also possible when the orbitals interact that the phase of one orbital is the opposite of the phase of the other. So one has a positive phase, one has a negative phase. In that case, you get destructive interference, and you get a node between the nuclei. It won't result in a bond. Okay, so so you see, chemists think of bonds. There's two ways the orbitals can come together: either reinforcing one another, resulting in bonding, or canceling each other, resulting in no bond formed between the nuclei. So here's kind of a picture for the hydrogen molecule. You have two hydrogen atoms. The electrons in the hydrogen atoms are in a 1s orbital. You see they're spherically shaped. And when they come together, when they get reinforcement, constructive bonding, you get a molecule look like this, where the two electrons are really spread. They're spread over the whole molecule. That's called a molecular orbital, where most of the electron density is between the two nuclei represented by the balls, right? So these molecular orbitals, you know, the language we're using is a part of the language of molecular orbital theory. And in molecular orbital theory, as I'm suggesting, whenever two orbitals come together, two atoms come together, their two orbitals result in two molecular orbitals being formed. You can either have the orbitals interact in a constructive way, where the orbital phases are where the orbitals are in phase, or they cannot. They can cancel each other. And so if you look at two hydrogen atoms over here, look at two hydrogen atoms over here. Each hydrogen atom has a 1s electron and an s orbital. So when those two orbitals interact, they can interact in two ways: either reinforcing, that results in a bonding molecular orbital, or they can cancel. There's interference, they're out of phase, and that results in what we call anti-bonding molecular orbital. And you notice in the anti-bonding orbital, there's out of phase. You see, there's no electron density between the nuclei. There's no bond. But we only have two electrons between the two hydrogens, right? One from each hydrogen. So they both go in the molecular orbital. And so the H2 molecule is a stable molecule where the two electrons are in the bonding molecular orbital. Okay? So if you look at helium, He2, you would think, well, does He2 exist? Well, helium has two valence electrons in each of its 1s orbitals. So I'm showing the 1s orbitals of both helium atoms. And so when these orbitals interact, you have two orbitals, so you end up always with two molecular orbitals, as we've described. a bonding molecular orbital, and an anti-bonding orbital. But now we have four electrons in the system, right? And remember, orbitals can only hold a maximum of 2 electrons. So 2 of the electrons go in the bonding molecular orbital, and the other 2 have to go in the anti-bonding orbital. And so the result is that the anti-bonding cancels the bonding, and there's no net bond. So this is like a one bond. This is like a negative bond. So they cancel, and there's no net bond, and that is why He2 does not exist. And this is a simple example of the power of molecular orbital theory, because it would be very hard, difficult, or impossible to understand otherwise why helium-2 does not exist. So it's a very general and powerful theory. Now, having said all that, we're not going to use molecular orbital theory very much in this course. Here and there, we will use it when it provides some insight, some understanding that we can't get from the other theory that we will use. We will use to a great extent, which is valence bond theory. So the bottom line, molecular orbital theory is more general and more fundamental, but you'll see valence bond theory, and you probably saw this in general chemistry. It's extremely useful, it's more intuitive, and it's much more easily to visualize. And that's the approach that typically is taken in organic chemistry, especially in this course, okay? So we will see it's a very, very powerful theory. So let's get going. Let me take it back to Gen Chem again, and we'll look at methane CH4. Here's methane CH4. Please, of course, you feel free to ask questions. It's a good idea to ask questions, if nothing else, to slow me down. But generally, if you have a question, I'm pretty sure a lot of other people will be grateful that you asked it. So methane CH4. So here are the valence electrons of methane. These are the valence electrons in the outermost shell. Valence electrons, remember, are the electrons in the outermost shell, and there's 4 of them. 2 of them in the 2s orbital, and 2 of them are in 2 of the 2p orbitals. But it turns out, to explain the bonding and structure of methane, you can't use these atomic orbitals. I'm not going to go into why, but it turns out using the atomic orbitals for bonding is not consistent. Was not consistent with what is known about the structure of methane. So what happens instead is this is a mathematical construct, is those 4 valence orbitals mix, they hybridize. And I'll show you on the next slide how they hybridize. So they hybridize. So here are the 4 in the box. Those are the 4 atomic orbitals. They mix to form 4 hybrid orbitals. Okay. No matter, you always end up with the same amount of orbitals you started out with. So we start out with 4 atomic orbitals, a 2s and 3 2p's, and we end up with 4 of these hybrid orbitals. They're degenerate orbitals, meaning they're the same energy, and they're called sp3 orbitals, which is a great name for it because it's constructed from 1 s-type orbital, right, the 2s, and 3 p-type orbitals, the 3 2p's. Okay? So you form these 4 sp3 orbitals, and this is what the orbital looks like down here. Okay, this is an orbital made from 25% of it is an s-type orbital, and 75% of a p-type orbital. And the advantage of this orbital is that most of the electron density is directed in one direction. You see, most of it is direct. You see, it's all kind of concentrated in this direction. to a much greater extent than the orbitals in an s orbital, which are kind of spread out spherically, and the electrons in a p orbital, which are kind of spread out equally in two directions. And the advantage of concentrating the electron density in one direction is that you can end up forming stronger bonds. So hybridizing the orbitals results in the ability to form stronger bonds, all right? So we have these four degenerate equal energy sp3 orbitals. And then those orbitals, so here's a picture where you have the central carbon, and here are the four orbitals. Now notice I didn't, the actual orbital, if you remember, kind of looked like this, right? Or like that, right? I've left out the back lobe. There's a small back lobe just because otherwise the diagrams get really cluttered and you don't lose any information by doing that. So we have our four orbitals and their electrons in these four sp3 orbitals, and they arrange themselves to minimize the repulsion between the electrons. Right, electrons are negatively charged and they would repel each other. So they get as far apart from each other as possible. And that geometry is a tetrahedral geometry, right? Where the bond angles between these orbitals are 109 degrees. 109 degrees, right? In that way, the electrons in those orbitals are as far apart as possible. And a tetrahedral structure is a pyramidal structure. You have three sides that are equilateral triangles, and the base is also an equilateral triangle. The carbon is in the middle of the pyramid, and the bonds radiate to the corners, the four bonds. Okay? So that's a tetrahedral geometry. And now the bonds in CH4, you have four hydrogens. The hydrogens, the electrons are in 1s orbitals. So the bonds are just going to form with the 1s orbital of the hydrogen atom overlapping or interacting with the sp3 orbitals of the carbon, right? That's it. So this is the final kind of structure from an orbital point of view, all right? So these
Professor,
bonds, yeah, please.
Why do we have a 109 degrees and 109.5 degrees? Is there a mistake?
No, good question. The actual angle in methane is 109.5, but I got lazy there. I rounded it off to 109, but it's technically the tetrahedral angle when it's symmetrical like this is 109.5.
Thank you, sir.
Thank you for the question. Okay, so we show the methane molecule with lines, right? This shows the two shared electrons, and here's kind of at a deeper level where you're showing the orbitals that are interacting to form those bonds. Okay. All right, so let's look at the next slide. So here are three terms that are useful. I'll define them for us. One is the steric number. The steric number around an atom is just equal to the number of atoms and lone pairs attached to the atom, all right? I'll give some more examples of that in the next slide, I think. So you look at the atom of interest and you add all the atoms, you add up all the atoms bound to that atom and any lone pairs attached to the atom. That's the steric number. So with methane, the steric number is 4 because you have 4 hydrogen atoms attached, right? The electron group geometry is the geometry of the orbitals around the atom, right? And we just got through describing that those orbitals arrange themselves in a tetrahedral geometry so that the electrons in those orbitals can be as far apart as possible, right? So that's a tetrahedral electron group geometry. That refers to the geometry of the orbitals. And then there's finally what's called the molecular geometry. And The molecular geometry is defined only by the position of nuclei. Now, in this case, all 4 positions of the tetrahedron have hydrogen atoms on it. So there are hydrogens at each position. So the molecular geometry in this case is also tetrahedral. But I will show you when we look at ammonia and water that the electron geometry and the molecular geometry can be different. And you'll see it, I think, once I show you those structures, okay? Okay, so steric number, electron group geometry defines the geometry of the orbitals around the atom, and the molecular geometry, which is defined only by the nuclei. So let's look down here. Oops, did I do something here? Yeah. So I'm going to look. I just look down here at these structures. So I have methane, ammonia, and H3 and water. So let's calculate the steric number of each, right? So there are 4 bonds or 4 atoms and no lone pairs around the carbon, so the steric number is 4. And then ammonia, you have 3 bonds or 3 atoms attached to the nitrogen, and you have 1 lone pair. That's steric number 4, right? And water, you have 2 bonds, 2 atoms attached, and 2 lone pairs. 2 plus 2 is 4. So that's also steric number 4. So all these methane, ammonia, and water all have steric number 4. And so here's the rule. If steric number is 4, then the atom will use sp3 orbitals. It will use four sp3 orbitals in the bonding. Okay, we can just focus on that now, but you'll see in a few more slides that if the steric number is 3, then it's going to use sp2 hybrid orbitals. And if the steric number is 2, it's going to use sp hybrid orbitals. But we can hold off on that. Let's just focus on the sp3 orbitals. Okay? And the reason that you're going to use 4 sp3 orbitals is because the bonds, yeah, you need orbitals to form bonds to atoms, right? But you also need orbitals to hold the non-bonded electrons. So here, I'll show you in the next slide what this looks like. So here's the next slide. And here's methane on the left side. And this is a ball and stick model where the carbon is represented by the black ball and the white ball represents the smaller hydrogen. But you see, you have the 4 sp3 orbitals forming bonds to the 1s orbital on hydrogen, and that describes a tetrahedral geometry as we showed in the earlier slide, right? So that's not only is the electron group geometry tetrahedral, but the molecular geometry is tetrahedral. But when you look at ammonia, what ammonia is, it's the tetrahedral structure of methane, but one of the positions doesn't have an atom. You see, one of the positions has a lone pair. It's like taking the tetrahedral, the geometry, and having an empty, no atom in one of the corners of the tetrahedron. You just have a lone pair. And so what happens there is that the geometry collapses to a pyramidal structure. I'll show this again in the next slide. The bond angle is a little smaller because the electrons kind of take a non-bonded pair is diffuse and it takes up a little more space. And then with water also has a steric number 4, so it's built on the tetrahedral structure, but now 2 of the positions are vacant. Vacant, when I mean vacant, there are no atoms there. They're just lone pairs. So when you have 2 of the positions of the tetrahedron with no atom, it collapses to a bent structure. That's the bend. It collapses to a bend structure. And the angle is actually a little smaller, 105, because these electrons kind of repel each other a little more than electrons in bonds. And that compresses this angle a little bit. So we have three geometries that are derived from the tetrahedral structure. We have a tetrahedral structure when all four positions have atoms in it. We have a pyramidal structure when one of the positions of the tetrahedron has a lone pair rather than an atom. And we have a bent structure when two of the positions of the tetrahedron have lone pairs rather than atoms, right? So this is all based on the steric number 4 requiring 4 sp3 orbitals to generate the structure.
Professor?
Yes.
I'm
Please.
imagining the compound hydrogen fluoride, where
Yes.
I'd imagine we'd also have the sp3 orbitals going on. Of course, it's a linear structure, but I'm wondering what's the angle between the valence electron pairs?
That's a good question. Yeah, you're right. What everything he said is right. The only thing is they're really, to have an angle, you need 3 nuclei. You need 3 atoms. An atom, so you see with HF or a diatomic molecule, there's no angle here. You need a nuclei. You can't define an angle between, that includes a lone pair. So, but everything, you're right. The lone pairs here would be in sp3 hybrid orbitals. You'd expect them to be in sp3 hybrid orbitals.
Thank you, Professor.
Well, thank you again for your question. All right, so let me look at the next slide. So this is a summary. For now, I think all we'd have to do is focus here. This is a summary of kind of what we said. And by the way, the book, you can learn all this in the book. And I encourage you to attend Juan's SI sessions and/or office hours. You can also come see me. He has great problems, and you get more practice and more support and help. Okay, so here are the 3 cases. So these all have steric number 4. Right? Methane we saw is its 4 bonds, steric number 4. Ammonia had 3 bonds and 1 lone pair, steric number 4. And water had 2 bonds and 2 lone pairs, steric number 4. So steric number 4, you need 4 sp3 hybrid orbitals, right? You got to, because bonds, to form a bond to an atom, you need an orbital, and to hold an electron pair, you need an orbital. So the electron pair geometry, those 4 orbitals are going to adopt a tetrahedral geometry to get as far apart as possible. But the molecular geometry defined by the position of atoms or nuclei is different. For methane, it's tetrahedral. For ammonia, it's pyramidal or trigonal pyramidal, because one of the tetrahedral positions is vacant. There's no atom there. And water, with 2 positions vacant of atoms, has a bent structure. Okay. So I want to show you a structure now, some structures, and we'll predict the geometries. I think that's what's next. Yeah. So this involves audience participation, class participation. So I will point to an atom and you'll tell me the geometry, all right? I have a few more. So what's the geometry around, the molecular geometry around that carbon?
Tetrahedral.
Tetrahedron, thank you. And what's the molecular geometry around the nitrogen?
Trigonal planar.
not trigonal planar.
Trigonal pyramidal.
Yeah, trigonal pyramidal or pyramidal. There is a trigonal planar geometry, but that corresponds to steric number 3. We'll see. So this is, I just abbreviated pyramidal. This we said was tetrahedral. And of course, the geometry around the oxygen.
Bent.
Thank you, Ben. All right. Okay, so now here's another structure. All right. Now tell me, what's the geometry around that oxygen?
Pyramidal?
Planet.
That's right. Thank you very much. That's pyramidal. Well, let's go over that. That's good. So you see there's 2 levels of this problem, really, because you have to determine steric numbers, you have to know if there are any lone pairs, right? And a positive oxygen, if you either remember or you can do the circle method, positive oxygen has 3 bonds and 1 lone pair, right? If you don't remember that, just do the circle method and you can calculate lone pairs. So the steric number is 4. You have 3 bonds to this oxygen and a lone pair. Whenever you have a steric number 4, it means that oxygen uses 4 sp3 hybrid orbitals. So the electron geometry is tetrahedral, the electron geometry. But one of the positions of the tetrahedron does not have an atom, it's vacant. And so that geometry collapses to what was correctly noted, a pyramidal structure. Good. What about this nitrogen? What's the geometry around that nitrogen, the molecular geometry?
Tetrahedral.
That's right. Very good. But there are 4 bonds to it. It's 4 bonds. So that's tetrahedral. That's right. Don't fall into the kind of the easy trap that the neutral geometries around Cn and O apply when those things have charges. They don't. So let's look at one more. NH2. I'm going to erase the. Can you see this? Yeah, I guess I don't have to erase it. So what's the geometry around that nitrogen?
Bent.
That's correct. Thank you. It's a bent structure and the 2 levels. First, we have to calculate lone pairs. So you can either remember negative nitrogen has 2 bonds of 2 lone pairs, or you can do the circle method. But you need to do that, especially when we introduce sp3 and sp hybrid. You'll need to check if there are any lone pairs. So 2 lone pairs, so steric number is 4, right? The electron group geometry is tetrahedral. The molecular geometry, as correctly noted, is bent because the tetrahedral geometry, 2 of the positions are vacant without atoms, right? So it's very powerful. I mean, look, and we didn't talk about bond angles, but we kind of know already what the bond angles is. We know these bond angles are going to be a little less probably than 109. We know a lot about the molecule in this approach, right? So I am going to, I'm trying to, I'm not stopping the lecture, but I want to stop the recording.